In the last video, we have already seen the theory part of linear regression. Now let's go into the mathematical details. So if you guys carefully remember, what is the first step? Our first step in any of the machine learning algorithms is hypothesis. And what does this hypothesis signify? Like hypothesis is the one which we tell to the model what it should do. Okay. Or we'll tell that this is the relation that it is between the input and output, and means we'll not tell exact relation, we'll just tell like draw some straight line, we'll not say how you should draw. Okay, so that is the basic point over here. So what will be the equation of straight line? If you guys remembered, like it will be y equal to mx plus c. So this will be our equation of straight line, and there are several notations in writing this hypothesis. Someone can write y equal to mx plus c, and some other guys can write y equal to theta naught plus theta 1x, and some other guys might write it like y equal to h theta of x equal to theta naught plus theta 1x. Okay, so these are several notations, so don't confuse with these notations. Okay, for now let's consider our equation of line as y equal to mx plus c. So this we are considering for now. Okay, in future I might be using this or this, but don't, please don't confuse. Okay, so this is our hypothesis equation, and let's see how this line will change according to the changes in M and C. So let's say this is our y and this is our x. So let's say if y equal to mx plus c is our line equation, and in this equation, if c is 0, if c is 0 and m equal to 1, then what will be our line equation? So if we substitute this c equal to 0 and m equal to 1, then it will be y equal to x, right? So we are keeping 1, so y equal to 1 into x plus 0. So y equal to x will be our equation. And how will that line look like? How will this line look like? So for point 1, we'll be getting the output 1, means those intersection point will be over here. And for point 2, the output will also be 2. That means x equal to y, right? So if you combine these 2 points, we'll be getting one line. And for that line, what will be the C and M values? The C and M values are C equal to 0 and M equal to 1. And let's take some other values. So let's consider C again as 0 and M to be 0.5. In this case, what will be our hypothesis? So in this case, if we substitute M equal to 0.5, it will be 0.5 times x plus 0. So overall, it will be 0.5x, right? So in such case, how will our line look like? Well, let's take some other color. For 1, it will be giving us 0.5, and for 2, it will be giving us 1, and for 3, it will be giving us 1.5. Like that, these points will rise. So if we draw the line, it will touch these points. Okay, so it will be C equal to 0 and M equal to 0.5 line. Okay. And let's try to observe some other line, that is C equal to 0 and M equal to 2 line. So for this line, how will it look like? It will look like this, y equal to 2x. And for this also, let's draw the line over here. So for 1, what will be its y value? It will be 2. And for 2, what will be its y value? It will be 3 here. Let's say 3 is over here and 4 is over here. And for 2, it will be 4. Okay. So our line equation will be connecting these. So like that, this equal to 0 and m equal to 0.2 will look like. Okay. So let's erase this. So these are our lines with C value 0 with different M values. Okay. So these are different lines that we are having. So if we carefully observe with the change in these M values, let's see how these lines are changing. If we are decreasing M value, then it is coming near to x-axis. And if we are making it to be 0, then it will touch the x-axis, right? And similarly, if we are increasing, it is going near to y-axis. Like that, by changing this M value, you can rotate this particular line in all possible directions. So for some specific M value, you can get a line like this, which is greater than 2 most probably. And similarly, for some other m value and c keeping c equal to 0, you might get some line like this. Okay, Like that, by just changing these m values, you can rotate the line in all possible directions. Please visualize it. I can't tell m values for each and every line, so please visualize that. Just by changing these m values, like we can draw all possible lines. Okay. And similarly, let's try to understand this particular C value. So let's say we are having these lines it's only. Let's take this graph only. If we are keep here C is 0, right? That's why our graph is looking like this. Let's say if we are making C equal to 1 for suppose, then, and let's say in all these cases we are making C equal to 1. Okay. In this case, what will happen? This axis will shift in such a way that whenever c equal to 0, it will touch at this point. It will touch y at 0. Okay. Whenever c equal to 1, it will touch this particular y at 1. Okay. So let's see how this axis will change when we are changing c value. So previously, this is our like previously we are having x and y axis, and it is touching y at 0. Now after making C value to 1, these lines will look like this only. Means the line angles will remain the same. So let's see how this axis is changing. Like this, it will be looking like this will be our y-axis, and this will be our x-axis. And here we'll be having y0, and here we'll be having y equal to 1. Okay. Or here it will be 1 on the y-axis, and here we'll be having x-axis 1. So as c equal to 1, it is touching at this one point. So what this will C signify? This C will signify at what place it will touch the y-axis. Okay, at what place these lines will touch the y-axis, and what will M signify? M will signify like what will be the angle of line. Okay, simply. So with the help of the C and M, so if with the help of CNM, you can get all possible lines. So whatever line you can think of, all the possible lines, just by changing, just by changing these two values, we can obtain the we can obtain any line. Okay. So as we can like change these and we can obtain any value, we'll leave it to the model. So we'll give a generalized equation to the model, or we'll give a generalized equation that is our hypothesis, that is y equal to mx plus c, and we'll ask the model to adjust these m and c values so that like the line will be some optimal line. So if you are taking an example of some x and y, and our data is looking like this. Okay, so let's say this is our data. For this data, initially, like this might be the line that is drawn by the machine learning algorithm, then the loss will be very high. So it will be changing our line like this by changing these MNC values, because as I said, by just changing these MNC values, it can obtain any kind of line there. So here it will change the MNC values so that it will be better than this line. So we'll see how it will do and all. And after that, like this, like this, like this, it will adjust and it will reach the optimal line. Okay, optimal line is the one which is having minimum loss or minimum error. Okay, so this is the overall process. Now let's try to observe what is our loss function. So in the last class, I have discussed that our loss function is y actual minus y predicted. So this is the loss function that we have discussed in the last class. But if we carefully observe, there is a slight problem with this y actual minus y predicted. So let's say this is x and this is y, and this is the data that we are having. Okay. For this kind of data, if you are having, let's say, some hypothesis like this, initial hypothesis like this, the model has adjusted our initial hypothesis like this. So if we observe, this is our actual price, whereas this will be like where it will touch, right? This will touch the line at this point, and this will be our predicted price. So this is our predicted, and this is our actual. And what will be actual minus predicted value? Will it be positive or negative? Think of it. So actually is over here, that will be some 1 or 2, and this will be some higher value, right? So as the predicted value is higher, actual minus y predicted will be less than 0, because this is lower and this is higher, so this will be less than 0, right? And similarly, for this point, if we compare this point's actual value, this point's actual value is over here. Okay, so this point's actual value is over here, and this point's predicted value, where is it? So this point's predicted value is very near to 0. So this is predicted. So here in this case, what is y actual minus y predicted? It is greater than 0. In general, we'll not consider only one point loss, right? We'll be considering all the points loss. So if you guys remember, I calculated the overall loss like this. So in order to tell how much the overall line is making the loss, I'm doing some average on all the training data points, where here m is the number of training data points. Okay, m is number of training data points. What I'm doing, I'm calculating loss on all the points. And what is our loss function? This is our loss function, that is y actual minus y predicted. And this is sometimes positive and sometimes negative. So the problem is, when we are adding up all these errors, it will happen that these positives and negatives will cancel. So here there is some negative and here there is some negatives. All these negatives and all these positives will sum up and become 0. If it is becoming 0, what does that mean? We are telling the model that the error that line is making is 0. That means the model will think that this is the optimal line that I have drawn, and it will stop the training process. But that is not the one that we wanted, right? So what can we do? What is the adjustment that we can do in this case? So what we can do is we can simply adjust our loss function in such a way that everything is positive. That is y actual minus y predicted. So we can adjust our loss like this. So this is called as mean absolute error. So there is some small problem with this. The problem is this can't be differentiable. So if you are taking some absolute value, it can't be differentiable. That is the first problem. And this problem can be somehow avoided. This problem can be somehow avoided, but we'll be using some other loss function, that is mean squared error. So mean squared is our actual loss function, and we'll be using this. I'll be telling the reason for usage of this. So y actual minus y predicted whole square. So we'll be considering square term, okay, for calculating the error. So first thing is it is differentiable. Why is differentiation needed? Because in optimizer, I said that in optimizer we'll adjust these parameters, right? So while adjusting, so you might be thinking, what are these parameters? So here, how will the line get changed? By adjusting these MNC values, right? So model will adjust these MNC values. So parameters are the one which are the variables which are adjusted by model. So here M and C are adjusted by the model. M and C are the variables that are adjusted by the model. So we call M and C as our parameters in case of linear regression. Like that, in every algorithm, we'll be having some specific number of parameters. Okay, those will be adjusted. For adjusting those, we'll be using optimizer, and in optimizer, we'll be doing differentiation. Okay, so or we'll be calculating the derivative. Okay, so in such case, we should make sure that the function that we are using is differentiable. But as this is not differentiable, uh, like we are facing the issue, but this can be handled somehow because it is not differentiable only at one point, and that is at 0. Mod value is not differentiable at only 0, so we can handle somehow. But the extra advantage mean squared error is having, apart from being differentiable, is for larger errors. For larger errors, it gives higher weightage. So when when for some when for some data, if the error is very high, let's say this is the data that we are having, and for this data, initial line is like this. At this point, the amount of error is very huge, right? The amount of error is very huge. So for such things, it'll make sure that it'll try to minimize these kind of errors first, or this such big errors first. So it'll be penalizing the larger errors first, and then it'll be moving on to the slower errors. Okay, so that is the advantage of this particular mean squared error function. So basically, let's say if the error is 5, we are telling that the error is 5 square, that is 25. That means we are showing the error to be very high, right? And whenever it is very less, let's say 0.5, we are making it whole square, it will become 0.25. So that means that we are, for very less errors, we are saying that don't care that much, and for very, like for some higher errors, we are saying, or we are giving more importance. So here if you observe, for higher errors we are showing it as 25 as our error, and for lower errors we are making it even low. So the model will try to reduce this higher errors faster as the error is very high. Okay, so this is the basic idea of this mean squared error, and that's why we'll try to use this particular mean squared error. Okay, and our loss function is, finally our loss function for a linear regression is mean squared error, and that will be calculating on all the training data points. Here don't confuse with them, some of you might be thinking it as slope. Here m is number of training data points, and on all the training data points will calculate the error, and then we'll be averaging it. Okay, so this will be my loss function. Okay, this is our loss function. And after loss function, what is the next step? Next step will be our optimizer. And this optimizer will be adjusting the line. And how it will be adjusting it? It will adjust it by updating the parameters. What are our parameters? Our parameters are M and C. So these will be updated with the help of some algorithm called as gradient descent. So gradient descent is the algorithm which will help us in adjusting the parameters. Okay, so let's try to observe the formula for gradient descent. So according to gradient descent, if you're having m, the gradient descent on this will be m equal to m minus alpha times loss with respect to some particular theta. Sorry, loss with respect to m. And similarly, here it will be c equal to m minus alpha, sorry, c minus alpha times loss with respect to C. Okay. So this is the gradient descent formula. Like that, we'll be doing it individually for each and every parameter that we are having. So in case of linear regression, we are having only two parameters, that is M and C. That's why we'll be applying this gradient descent only for M and C values. If you're having multiple parameters, then we'll be doing it for each and every parameter. Now let's try to understand what is this particular thing that is signifying. So if we try to draw a graph between loss and theta value or m value. What is m? M is our parameter value. So if we try to draw a graph between m and loss, so before that, if we try to draw a graph uh, of x square, if x is this and x square is this, what will be our graph look like? Our graph will look like some parabola like this, right? So here, if we, what is our loss function? Our loss function is y equal to, or 1 by m equal to 1 to n, y minus y actual minus y predicted. This is our loss function, right? And what is our y predicted? Our y predicted is given by our hypothesis, right? And what is our hypothesis? That is mx plus c. So this loss function itself is a function of m and c. Okay. So this loss function itself is a function of m and c. So whole square will also be there. So if we make everything constant, for suppose just think that everything apart from like m, all are constants. So everything apart from, I'll write it again with another color, y actual minus mx plus c. So this will be our loss function. So if we make everything constant apart from m, by changing in this m value, how will the loss will change? So this is the only variable, right? So by changing in m value, our loss function will look like this. Our loss function curve will look like this. So this is the curve with respect to m and loss when remaining are constants. Means just think of it like that. And similarly, if we do with respect to c, similarly for c also at some value it will look like this. And this value we call it as m optimal, because for this value our loss is minimum, right? So that's why we call this as M optimal. And similarly, we'll be having C optimal as well. Okay. So we wanted to reach to this particular point because for what is M optimal, our hypothesis should come, ideally should come over here. That is M optimal times X plus C optimal. So we are trying to find this M optimal and C optimal. And what is this M optimal? This M optimal is this point. And similarly, if we try to draw the graph between loss and C, so if this is our loss and this is our C, that is our yeah, we have two parameters like M and C. So here we have drawn it with respect to M. With respect to C, if we draw, it will also look like this. Okay. So at this point, C is minimum. So at this point, we're having C optimal. So initially we might be having M, let's say our initial M value is 5, but M optimal is 10. That means M optimal is 10 over here and M initial M value is 5. So initially we'll be somewhere over here and here the error is high, right? So this is the amount of loss that we are having. So this loss is very high. So what we'll be doing, we'll be applying this formula. In this formula, what this is signifying, this will be telling us slope at this particular point of time. If you are drawing some tangent, and if this tangent is looking like this, anything like this or this, so so if the tangent is looking like this, then what does that mean? That means that it is negative slope. Or you can think of it in some other way, like if it is difficult for you to guys to understand, I'll tell it in some other way. So basically, like this is the shape, right? So at this point, at this point, slope is 0. And for all the points which are this side of this, the slope will be positive. So this side slope is positive, and this side slope is negative. So from this point, if we go this side, slope is negative, and if we go this side, the slope is positive. Okay. So here, as the point is over here initially, here if we do loss with respect to m, it will be giving us the slope at this point, and here the slope is negative. That means if we apply some negative number over here, we'll be getting some negative number over here, some negative floating point number, and that will be minusing from m. So if you are minusing with some negative number, what will happen? We'll discuss what alpha is. So you might be having doubt. So we'll discuss this later. So on multiplying with some negative number, it will become positive. So we are adding some specific value to m, right? So this is our m previous value. This m will be moving towards m optimal because here, as we are getting negative slope, we are able to add something to it. So this will be my new m value and this will be my new loss. So this is the previous loss and this is the new loss. Okay. So this like that slowly it will move and reach to the optimal. So this happened in one updation. Like that, we'll do several updations. Okay. After doing several updations, we'll reach M optimal. And similarly, let's say my initial C value is over here. Okay. And at this point, I'll get to know the slope by using this partial derivative of loss with respect to C. So as the slope is positive, so this value is positive, right? So we'll minus something from C. So that's why this previous C will move towards this C optimal and this will be my new loss. Okay. So this is the previous loss. So this is the previous loss and this will be my new loss. Like that, our losses will reduce, and our C value will move or will go to C optimal. Okay. And M value will go to the M optimal. And when this C value and M value reach to the optimal values, then that is the line that we wanted, right? At that point, training will stop. So now let's try to see all of these points at a time so that it will make more sense. Okay. So what is the first step? Our first step is our hypothesis. And what is our second step? Our second step is our loss function. And what is our third step? Our third step will be our optimizer. So these are the three steps. And what is it in case of linear regression? It is some line equation that is y equal to mx plus c. And what is the loss function that we are using? That is mean squared error, that is MSC. And the formula for that will be I equal to 1 by, if I'm using m, you might get confused. So I'm using L. So 1 by L, I equal to 1 to L, y minus y actual minus y predicted whole square. So when, from where this y predicted will come? That y predicted will come from over here. Okay. So this will be our y predicted. And what is the optimizer we'll be using? That we will be using is gradient descent algorithm. So with this, so if you think like theta has some parameter value, theta nu equal to, so this is the updated value, theta nu equal to theta old, that is the previous value, minus alpha times loss with respect to that particular theta. So like this, our gradient descent for all the parameters will be applied. So these three are the main steps. So initially, whenever we are initializing some linear regression algorithm, what the machine will do, the machine will assign random MNC values, random MNC values, and after that, we'll calculate the loss. Obviously, as the MNC are random values, loss will be very high. And when the loss is very high, we'll go to the optimizer. And optimizer, what it will do, it will signify, so this partial derivative will signify as the direction in which those particular theta values should move, or those particular parameters should move. So here, if you observe, so here, this particular partial derivative is signifying that move in this direction. And here, this particular partial derivative is signifying that move in this direction. Like that, this particular, simply you can think of it like this partial derivative is saying us direction in which parameter value should move. So this it is signifying. So we'll update it one time of like all the parameter values, that is MNC will get updated once, and after updating, so we'll again check the loss. Okay, so first first we'll initialize hypothesis, and then we calculate loss, and then we'll optimize the things. Once after optimizing it, we'll again check the loss. So like we'll again check the loss, and again the loss will be high. In one updation itself, loss will not get adjusted, right? So loss will be high. So again we'll go to optimizer, and what we'll be doing, we'll be adjusting the data values, and again we'll go back, and again we'll adjust. Like that, we'll continue this process. Till what time we'll continue? Till what time we'll continue this process? When this particular slope becomes zero, that means after several updations. So this is one updation that we'll do, like in one loss calculation. So after reaching this point, again we'll calculate the loss. That is, we'll see that loss is this much, and again we'll come to the optimizer and we'll do this. Okay. So like that, after several iterations or several updations, we'll reach the M optimal. So we'll reach M optimal after several updations. Okay. So this is the overall process. And when we reach M optimal, as the slope is zero, this process will stop. Or when it becomes like, we'll be having some threshold value when this like when this new and old are not changing very much beyond that threshold value. Let's say threshold value is 0.001. So if the difference between new and old value is less than 0.001, then obviously we'll stop the training process. Like that, this overall process will be working. Okay. So I hope this linear regression working is clear for everyone. If you have any doubts, comment down in the comment section. I'll be helping you with that. And I hope you enjoyed the video. Thank you, everyone.